Hello everyone, in this tutorial we're going to see how to manage the digital inputs and outputs in the development environment of Albatros using the programming language GPL. Starting off, we'll create a simple system, consisting of a single group, called group test, divided in two subgroups, called input and output. Within the subgroup input, we will create a digital input and call it button 1, while in the subgroup output, we will create a digital output and call it LED 1. Let's get to the heart of programming by writing down some simple functions in order to be able to manage these devices, as we haven't created any function yet inside group test. The screen we'll see when we open the group functions will be a blank sheet. Let's see some little basic notions we need to know to be able to start writing code. To write a comment, just write a semicolon. Anything after the semicolon in that line will be colored green, which is the color of the comments. So, we'll write first thing a comment explaining the group purpose. To create a function, the keywords are function and fret. Function is the entry point of the function, while fret is its exit point. Beside function we need to define the name of the function, that cannot include spaces. A useful trick to use names consisting of more words is to use capital letters for the first letters of every word. For example, if we want to call the function switch on LED 1, we will write the initial S, O, and L as capital letters. Now, let's try and save to see if everything is correct. As you can see, the compiler generated an error. The main group function is missing. Every group needs a function with the same exact name as that of the group. Then, we'll create the function group test and leave it empty for the moment. As a first example, we'll create a function whose purpose is to activate the output LED 1, so to switch on the LED light connected to it, and we will call it switch on LED. To sum up what's said so far, we have function name, function and fret. Now we need to write in what we want to do. To set an output, we use the instruction setout and the name of the output. Once we've written setout, as you can notice, the word becomes blue. This means that it is an instruction provided by the system that executes a specific command. In this case, the command is to set the port connected to the output. Selecting the blue word, if we press the F1 key, the help on the specific instruction will appear. Now, we're going to see which output we want to set, writing where to find it, then we'll enter the name of the subgroup followed by a dot and the name of the device. In order to avoid writing the directory for every device, the system gives us the possibility to directly select it. By pressing Ctrl and D we'll open the dialog window that lets us comfortably select the device and insert it in the code. As the aim of this first function is to switch on the signal LED, we have everything we need. First off, let's try to save, in order to check the presence of any error. With CNC initialize, we send the changes made to the numerical control, even in simulation mode. If we change the code, we need to execute CNC initialize in order to be able to test it. Let's see now if what we wrote really works. We'll select from the main menu the submenu test. In the submenu we'll click on Run function. Now, in the window dialog, we'll select the function we want to run and start it. We can then see if, by starting the function switch on LED, the output LED 1 is activated. As you can see, everything works correctly. A digital output can be set and reset even manually from diagnostics, by selecting it and double-clicking or by pressing the spacebar on the keyboard. As a second example, we'll create a function that will reset the output LED 1, we'll call it switch off LED. The instruction to reset a digital output is called reset out. In this case as well, if we select the name of the function and press the F1 key, the help on the GPL instruction will appear. So, we've created the function that will reset LED 1. Let's save, initialize, and test it. As a third example, we'll create a function that will set the output LED1. We'll wait 1 second, and we'll reset it. We'll call it on-off LED. We've just seen how to set and reset an output, but now we're going to have to add in the code a 1 second wait, so, using the instruction delay beside the time expressed in seconds. At this point the system goes to the next instruction after waiting the indicated time. As always, we open the help with F1. We've then created the function on-off LED, that activates the output LED1, waits 1 second, and resets the output LED1. All we have to do now is testing it. As you can see in this function, we've written some instructions that are not already being used by the previously created functions. We've created before a function that sets the output LED1, so, instead of writing it again, we can make a call of the function switch on LED. We can do the same for the instruction reset out LED1 by calling the function switch off LED that's been previously created. What will happen is that as first instruction we'll call the function switch on LED, we'll wait it ends setting the output LED1, wait a second, call the function switch off LED and wait it ends. At this point, we can exit the function. The function call is very useful, as it allows us not to write again identical functions, and most of all, in case of error, we know for sure that by solving the eventual error in the single function, we'll have it solved in all of the sections of the code that recall it. As a fourth example, we're going to create a function that will switch on and off continuously our signal LED in 1 second intervals, never stopping. We're going to call it blink LED, as seen in the previous function. We're going to call the function switch off LED and, at this point, we'll have to wait another second and rerun the code from the start. In order to do so, we'll create a label, writing the name of the label, in this case it's loop, and putting the colon at the end of the name. The word becomes red. This means that the system interprets it as label. We can define a label as a point within the function where we can go through a goto. In order to better understand its usefulness, we'll create the label loop at the start of the function and enter goto loop before fret. In this way, once the code gets to the end of the function, it will go back to the starting point, where we put the label loop. By doing so, when we run the function blink LED and meet the label loop, we pass to the next instruction. We call the function switch on LED, wait that it's ended. We wait a second. Call the function switch off LED. We wait it's ended. We wait a second. We meet goto loop and go back to the label loop, repeating the loop indefinitely. All we have to do now is saving, initializing, and testing our function. Test, run function, blink LED. As you can see, the output LED1 is repeatedly set and reset in 1 second intervals. Now we'll introduce an important tool that the system gives us, the debug. By clicking on debug task running, a window will open with all the tasks running at the moment. In this case we have only one, our blink LED. By selecting it and clicking on debug, we can finally debug our function. By clicking on debug stop now or alt and pause on the keyboard, the code is interrupted. We are making it advance one instruction at a time, with the F10 key in case the instruction is a function call and we want to run the function without entering it. On the other hand, by pressing instead the F8 key, we enter the function debugging it step by step. Once all of it is executed, we can go back to the calling function. It is possible to enter a breakpoint or interruption point in two ways, either by clicking with the mouse beside the gray space right to the line number, or from the submenu debug. A breakpoint implies a stop of the code in the point where it's inserted. It is useful when we want to debug a part of the code that's been just written, letting it run the previous parts already tested. If we want to stop the debugging, we'll press at the same time Alt and F5 on the keyboard, or, always from the Debug submenu, click on Interrupt Debug. Moreover, the system allows us to stop all running functions from the submenu test clicking on End. Instead, if we want to end only one function, as we're doing now, we'll go in the submenu Debug, click on Running Task, select it and click on End. As a fifth example, we will create a function that checks the status of the output LED1 and, according to the status, it starts an action. We'll call it setResetLED. Simply if the output is on we'll reset it, if it is off instead, we'll set it. To control the status of an output, the system gives us the instruction output. As always, by pressing F1 the help with the explanation of the instruction will appear. We'll write then output, followed by the name of the output and the status we want to check. In this case, if the output is on, we'll add then and we'll call the function written previously to reset it, called switchOffLED. If the status of the output is not on, we'll go on inserting else, meaning otherwise, checking in this case if the output LED1 is off. In case it is, we'll call the function to set it switch on LED. At this point we save, initialize and test the function. As we can see, when the LED1 is off, the function switches it on, while when it is on the function switches it off. We create now a function with the same purpose as the function blinkLED, that is to set and reset repeatedly with 1 second intervals the output LED1. We'll call it blinkLED2, but we shorten it by creating a loop with a 1 second delay around the function we have just created setResetLED. Let's go check that the functioning is the same as the function blinkLED previously created. At this point we enter in the next function the input button 1, creating an algorithm that sets pressing a button, releasing it and switching on a signal LED as a consequence. In order to do that, we'll introduce a new instruction called waitInput. The instruction waitInput, as it's easy to guess, waits for the status to occur in an input and then runs the code we're going to write. Let's write then waitInput, the name of the input, button 1 in this case, and the status we want to check, on in this case, supposing that the input is linked to a button contact that is normally open. In doing so, we intercept the pressure of the button. Now, to check the release of the button, we need to wait the off status of the input. We copy and paste the first row of the function and replace on with off. Once the second waitInput has been checked too, it means that the button has been pressed and released. Now all we have to do is switching on our signal LED, and we do so by calling the function switchOnLED. Now we need to test if what we wrote down really works. Let's go then debug the function and, by double-clicking on button 1, simulate pressing and releasing the button. As we can see, what happens is exactly what we expected. Let's make now a change to our function and update its comment. So far, we coded how to switch on the lamp if it's off, but we want to be able to switch if off with the same code if it's on. In order to do so, let's just recall the function setResetLED created previously instead of the function switchOnLED. Let's test the change, as always. Once the function has been checked, as a last change let's make the cycle continuous. To do so, as we have seen earlier, we insert a red loop label at the start of the function and a goto loop before the end of our function. This way, our code will go on testing if the button is pressed and released. Now, let's proceed testing this last change. Let us create now an input in our project, still in the group test. Inside the subgroup input we will create a second input and call it button 2. After creating it, we will link it in the virtual physical, a necessary step to inform the system about where the input is physically connected. Now we can create the function button12 that allows us to use both inputs by simulating a situation where, if button 1 is pressed, the signal LED will be switched on. If button 2 is pressed instead, the light will be switched off. Let's start writing this function by creating the usual label loop. Then we will use a new instruction, made available by the system, called if_input. That works the same way as the instruction if_put. Let's test then whether the input is on or off. So, we'll write if_input, then the name of the input button 1, checking that the status is on, then we'll switch on the light by using the function switch on LED. We'll add an else to the following line, and we'll do the same with the input button 2, but this time we'll recall the function switch off LED in order to put it on off. At this point, in the lines following the status check of the inputs button 1 and button 2, we will add a line with the instruction wait input in both cases, in order to wait for the input to go back to off after being on, therefore simulating the release of the buttons, as we've previously seen. At this point, we have coded a function where, if we press and release button 1, we'll switch the light on, if we press and release button 2, we'll switch it off. So we've created an on button and an off button. In order to make the function cyclical, we'll insert a line with goto loop before fret. Then, save, initialize, and test what we have written. In order to better test the cycle, we'll follow it in debug with a breakpoint on line 79. As you can see, the function executes exactly what we expected. Now let's pass on a new exercise, by creating a function called button 1 and button 2 that provides for the switching on of the lamp LED 1 if it's off and the switching off if it's on. In case both buttons are pressed and released at the same time, this function, 2, will always remain active. Then we will create the red label loop first, if the status of the input button 1 is on. We'll also check the status of the input button 2, if the status of the input button 2 is on as well, we'll wait, at this point, that both buttons are released, also checking the off status for both. In order to wait that the status of both inputs is simultaneously off, we'll introduce a new instruction made available by Albatross, called multi-wait input. We'll write then multi-wait input followed by button 1 and button 2. In order to work correctly, the instruction multi-wait input requires the creation of a mask, which we can find explained in detail in the help. The mask contains information on which inputs we need to wait. This is because, in some cases, we might have 3 inputs and depending on the situation, we only have to wait for 2 or 1. By typing the $, bitmask and B before the names of the inputs, we set a binary mask. At this point, we only need to add the status in which we must wait for them after the input names, that in this case is off. To sum up, if the button 1 is pressed, we will proceed by checking that the button 2 is also pressed. We'll wait for both buttons to be released by using the instruction multi-wait input and the bitmask. At this point, we'll call the previously created function setResetLED, whose purpose is to change the status of the output LED 1 from off to on and vice versa. We'll close the if input with the end if, and finally, we'll enter the jump to red label at the start of the function with the usual goto loop. All we have to do is saving, initializing, and testing our new function. First thing, we'll check that by pressing and releasing the single buttons, not at the same time, the output doesn't change its status. Now, we'll check that, instead, by pressing and releasing them at the same time, firstly by forcing both the inputs on and then by forcing them both on-off. The output LED 1 moves to on. Now we'll follow the function in debug by simulating the opposite, that is, that following the same operation, this time the function setReset LED takes the status of LED 1 to off. Now we'll create a function with the same purpose as the previous one. We'll call it, indeed, button1 and button2_second. However, in this new function we'll use an instruction that we haven't seen yet, called if and. This instruction compares the status of two devices, and it's satisfied if the status of both devices is the same as the one specified. We'll write then that if the status of button 1 and button 2 is on, then we wait for the release of both buttons by using the instruction multiwait input, already explained above. At this point, we'll switch off or on the signal LED by calling the function setReset LED. As usual, we'll save, initialize, and test that the function meets our needs. After checking the correct working of the written function, we'll create a function that provides for the switching on or off of our signal light, even if only one of the two buttons is pressed. We'll call this function button 1 or button 2. In order to do so, we'll use another instruction, called if or, that compares the status of the two devices like if and, but differently from the instruction if and, it is satisfied if the status of at least one of the two devices is equal to the one specified. We'll write then if or followed by the names of the two buttons and the status we want to verify, which is on in this case. Then we'll wait for the buttons or the single button to be released, by using the instruction multiwait input that checks the off status, and, as previously done, we'll recall the function setReset LED in order to switch on or off our LED. In this case as well, as you can see, our code in debug mode works correctly. For the next exercise, we'll add to our project 4 new outputs, that will simulate as many signal LEDs, that we'll call LED 2, LED 3, LED 4, and LED 5. Once created, we will link them correctly in the virtual physical. The function we're going to create now does nothing new. Its function is just to switch on all the signal LEDs that we've created and linked in our project. We'll call it setAllLED. Now, we'll write 5 setouts in 5 separated lines, where we'll activate our LEDs, from 1 to 5. Let's check their functioning quickly. And now we'll create a function whose purpose is to switch off all our signal LEDs, and we'll call it resetAllLED. We will write then 5 reset outs in 5 separated lines and reset from LED 1 to LED 5. In this case as well, let us check the functioning of these new code lines. Let's see now how to get the same result by transforming our two functions, each one consisting of 5 lines, into 2 functions, each one consisting of 1 line. In order to do so, Let's use the instruction multized out in the function set all LED. The aim of this instruction, as it is easy to guess from its name, is to set more inputs at the same time. Exactly like the instruction multi-wait input, the multized out needs a bit mask to determine which outputs to set. We'll write then multized out followed by the binary mask and the names of the 5 outputs from LED 1 to LED 5. To review it briefly, we will type the $sign, the bit mask followed by the letter B. We'll write a binary mask where each single bit can have value 1 or 0. In this case we must set all the outputs, so we'll write $11,111 and B. By highlighting them, we'll see which bits refer to which device. Let us cancel then the 5 lines previously written. In the function reset all LED we'll use the instruction multi-set out that, differently from multized out, resets more outputs at the same time. This one too needs the bit mask to function. All we have to do now is saving, initializing, and testing if what we have written is correct. As you can see, our code runs correctly. An important difference we have to point out between using 5 lines of code with as many set out instructions, one after the other, instead of one single line with a multized out for 5 devices, is that, in the first case, the outputs are set one at a time. Even if in this case the code is executed very quickly and with few devices, we hardly notice it. On the other hand, by using the instruction multized out, the outputs are set at the same time. The same is true, obviously, for the instruction multi-set out. In order to better understand what we can do using the instruction multi-set out, let's suppose we want to create a function that sets only LEDs 1, 2, and 3. We'll call it setLED123. To satisfy our needs, all we have to do is changing the bit mask, writing then the $sign followed by 00111 and B at the end. As you can see, the code only switches on the LEDs with value 1 in the bit mask. I hope this video may have helped you. I invite you to browse in our YouTube channel or in our Facebook page, where you'll find more tutorials of TPA software or of more applications.